Here, when you solve the remaining problems in the assignment, the directions given in verse relation, the answers are given in the book. So, questions where the answers are not there in the assignment sheet. So, you can easily verify those solutions. We discuss them later, but I will continue with the topic of mass transfer. We saw that just as I'll take up the discussion on the control volume rather than the material volume, because that's a bit difficult to for the single component C equal to 1, we saw that one form of the continuity in the control volume representation was simply, it means that the rate of change of mass within a control volume represents the mass in the control volume at any instant of time. So the time rate of change of that is the net mass Fx, the negative of the net mass Fx. That is this, right? So this gives in minus out, and this would be the accumulation term. Now, as an extension of this idea to where we have more than one component, we could say that the time rate of change of the mass of species alpha, right? So we now have alpha equal to 1 to C. So we have to write the continuity equation for each of the C components. This may be given again as a net mass Fx of, or the net mass influx of alpha to flow into the control volume. And plus an additional term which will not be there in the single component, which is the rate of generation, net rate of generation of alpha through chemical reactions. That is the other term. And so, when this may be shown to be equivalent to the local continuity equation, which is very similar to the, except for the additional term. So, this is for the single component, which is equal to 0 here. Whereas here, you will get the additional component, the term R alpha, where R alpha may be regarded as the net rate of generation of species alpha to chemical reactions. The units of R alpha are clearly mass of alpha per volume per time. So this is like a rate density, generation rate density per unit volume per unit time will be there. When it's integrated over the whole volume, you get the rate of generation of alpha within the control volume through chemical reactions. So are these ideas clear? The only new thing here is the fact that we have to allow for generation or transformation of alpha as well as transformation of other components to alpha through chemical reaction. And so we get that. Now, further representations of the continuity equation are available in the literature. The first step is to express the continuity equation in terms of the weight fraction W alpha. It's a mass fraction actually. So using M alpha, we might be confused with the mass of alpha. That's going to write W alpha, which is defined as rho alpha by rho. The rho is the total density given by, we want to express this in terms of the mass fraction. That's a more natural variable in, or the mole fraction, which we take up later. The weight fraction is a more often used composition variable rather than the density of species alpha. And also, we want to introduce a new quantity which is called as the diffusive velocity associated with species alpha. I will define it shortly. Now what I will do is I add up what we get. We add up all the C continuity equations. Then I get d by dt. So I can take the sum in and out of the derivative term. Plus, this will give the motivation of defining a mean velocity or an average velocity for the mixture. So sum equal to sum over alpha equal to 1 to C R alpha. Now here you can easily see that even though this represents a net generation of mass through chemical reactions for all the components, so that has to be clearly equal to 0. So they take it that the chemical reaction that we are considering cannot generate overall mass cannot be generated, right? So this will have to be equal to 0. When you write in terms of moles, the number of moles due to chemical reaction can change, but the net mass generated through chemical reactions would have to be 0, right? So based on that principle, I can now define here the total density of the mixture as alpha equal to 1 to C rho alpha. I also define a mean velocity. This will be called as the mass average mean velocity. That is simply given by V, and that is defined as sum over by an average velocity, which takes into account the velocity of all the species. And so with this definition, it can be also written as sum over W alpha B alpha. The definition of W alpha B, weight fraction or the mass fraction. So with this, now I can write the continuity equation for the overall motion of the mixture like this. This is merely a consequence of each of the C continuity equations, and using the fact there cannot be while particular species may be generated, the overall mass generated in chemical reactions has to be C. Mass is conserved in that overall sense, right? You cannot generate. This is, effectively saying that when we balance the reaction, we take into account of that's a different principle. We take into account the fact that the balance is maintained for each atom through chemical reaction. But if you add up all of that, right, so effectively you can see that the mass will be conserved in chemical reaction, total mass. Right? So chemical reactions cannot lead to a generation of increase in mass. So we get this equation, which is sort of a consequence of these equations. But the interesting thing is that it looks very much like the continuity equation of a single component, except that now the rho here is to be interpreted as the sum of the densities, and the mean here is to be interpreted as the mean velocity, which is defined like this. When you define these quantities, then we get that the continuity equation of the mixture as a whole, we can say, is resembles that of the single component continuity equation in form. Right? So now we define these quantities. Now the U alpha is defined as P alpha minus B. That is what is called as the diffusive velocity. Rewrite the continuity equation and take a particular component alpha in terms of those variables. So clearly I can write rho alpha is W alpha times rho, right? And then rho alpha B alpha can be written as, in terms of the diffusive velocity, can be written as rho alpha U alpha plus rho alpha times B. So now we get d by dt of rho alpha will be W alpha times rho plus the divergence. Rho alpha B alpha can be written as the divergence of rho alpha U alpha plus the divergence of rho alpha B. And that is equal to R alpha. That will remain as because I'm not talking about a particular continuity equation. So I can now simplify this as I'm going to treat this and we will give this a name, and this will be called as the diffusive flux of alpha. I'm sorry. We give another, introduce another quantity. This is referred to as a diffusive flux of alpha. I explain the physical significance of these quantities, why it is important to introduce these. And so I can write this as J alpha. So I want rho alpha out of the picture. So I can write this as rho W alpha B is equal to R. So now I will look at this. This can be written as W alpha times rho B, divergence of a vector, which is actually product of a scalar times another vector. So this vector I will focus as rho times B, applying the rule on the divergence, scalar times a vector. So I get again all of these terms. Also a vector is flux. I will write this as W alpha times the divergence of rho B plus rho B dotted with, right, the gradient of W alpha. That is equal to R alpha. So now I will combine these two terms. These two terms as W alpha times dρ by dt plus, and that is 0 as we have already shown. Right? So then I can combine these two terms and write this as rho times dW alpha by dt plus B dotted with the gradient of W alpha is plus the divergence of the diffusive flux is equal to R alpha. Now if you look at this form, this has the form of d by dt plus B dotted with something. So I can introduce a substantial derivative, right? D by dt can be defined as d by dt plus B dotted with the radius of whatever quantity. So from this, I can write the continuity equation. So this compact form, namely that the substantial rho times the substantial derivative of the mass fraction plus. So the reason for writing it in this form is that the often the models are introduced for the diffusive flux in terms of the Fick's first law. It's always a question. There's so many fluxes that are defined in books. It's important to understand the distinction between them. Now I have here the first diffusive flux. This will be regarded as the mass diffusive flux based on the mass average velocity. There are many other average velocity which we can define. For instance, when we go to the molar case, right, I can write the whole equation in terms of the molar density and the mole fraction. That's also sometimes useful when you deal with diffusion of gases. It's convenient to use the mole fraction representation. We will see there that a different diffusive flux and a different average velocity would be introduced. So, to keep this in mind, we try to express now the equations in terms of the moles rather than the mass. Right? So, for that, I have to introduce certain other variables, namely the molecular weight of each species. Right? So, I will start with this. Moles per volume, that is defined as rho alpha by m alpha, that's C alpha. And I define the total concentration as sum over alpha into 1 to, here I have to distinguish to capital C, C alpha. Distinguish between the lowercase c, represent the total concentration in terms of moles per volume, as opposed to the total number of components, which I am calling it as C, the uppercase C, larger than that. So, right. So, and then I define the mole fraction as C alpha by C, the mole fraction of component alpha. Then normally when we talk about mole fractions or weight fractions, we are talking about a closed system which is uniform. Right. So, we say mass fraction is mass of species alpha divided by the total mass of the system. But here we are dealing with a case where the densities are actually varying with position and of course with time. So we need to carefully define these mass fractions and mole fractions. So the mole fraction will be defined for continuum mechanics of mixtures by these quantities. The local concentration of species alpha, molar concentration divided by the total concentration. That would be the definition of the mole fraction. You can also get relationship between the mass fraction and the mole fraction and so on. For instance, the relationship, because I have rho is equal to alpha to 1 C, rho alpha, which I can now write as 1 to C, C alpha m alpha, okay, which can be written as C times x alpha m alpha. And this is sometimes referred to as the average molecular weight. It's actually a function of the composition. Average molecular weight is sum of alpha equal to 1 to C, mole fraction of alpha times the molecular weight of alpha. So I can get this important relation rho over C is equal to m average. All of these follow just from definition. So I can write also rho alpha by C alpha as m alpha. And then you can easily see that W alpha, which is rho alpha by rho, W alpha by x alpha is rho alpha by rho divided by C alpha by C, which then can be written as m alpha by m average. We get all these relations from the definitions. Clear these definitions and the various relations that follow from them. I would rather not remember. I mean, these are basic things everybody knows. defined. The rest of the things can be very easily obtained. Right? So now to get in terms of the mole fractions and the molar diffusive fluxes, right? So I will simply have to divide this by the molecular weight of species alpha that I get as a constant. Right? So I divide through. I simply get dC alpha by dt plus C alpha B alpha is equal to R alpha by M alpha, and I will call this the R alpha, the lowercase r representing the molar generation of species alpha. That is moles per volume per time. The typical Ra, Rb, etc. that is defined in reaction engineering textbooks. Right? That is what it is. Now, if I add all the equations, again alpha equal to 1 up to C, if I add all of them, then I get dC by dt plus C. Now I am going to define a new variable which is the molar average velocity, and that will be defined as sum over C alpha B alpha divided by C, or given by X alpha B alpha. So when the velocities are weighted by the mass fraction and added, I get the mass average velocity. The velocities of the individual species are weighted by the mole fraction. I get the molar average velocity. Right? So clearly that would then be the sum over alpha equal to 1 to C alpha B alpha, that would be B star. Right? And this though, when you sum over it, there is no constraint on the molar generation. That need not be seen. You can always generate moles of species, but that is not concerned. Right? So then I will simply have to leave it as alpha equal to 1 to C R alpha. It will remain as it is. Next to in terms of the moles, then you don't quite get the whole thing adding up to 0, that you have to remember. If I can write for the single component, I can write dρ by dt plus the gradient of rho b equal to 0. Can simply be replaced by dc by dt plus the gradient of cb equal to 0, single component. For multi-component, you do not have the same form. This is merely a way of defining, somehow leads to a certain resemblance between the overall continuity equation and the continuity equation for a single species. I don't think too much significance will be attached to that. Right? So now, I want to express these in terms of the mole fraction. So here, I am going to go introduce, will be convenient, you will see the reason behind it. I now introduce another diffusive flux, which we call as U alpha star, and that would be V alpha minus V star. All these are vectors. So this is a diffusive velocity scalar, right? Which is the velocity of species minus the molar average velocity. Clearly, the molar average velocity need not be equal to the mass average velocity. And then I will define another diffusive flux, which is C alpha times U alpha star, which is the molar diffusive flux with respect to the molar average velocity. So I can add that here. So you can clearly see with this definition you can construct two other diffusive fluxes which are not that common. So I have the second one. So the star here, so this is a change in notation. I'm using the capital J, so that would mean that I will use C alpha, that is the molar diffusive flux. The star refers to which average velocity with respect to which the diffusion is considered. So what you have to understand is that here normally we directly introduce the Fick's first law, right, which says that the diffusive flux actually is proportional to some kind of a concentration gradient. We associate diffusion with a concentration gradient. That's not very general. A general viewpoint is diffusion. The reason why these are called diffusive fluxes, we say that species alpha is diffusing means B alpha minus B is not equal to 0. That means the species is moving with a velocity alpha, B alpha, which is not the same as the average velocity. Right? So when that happens, we say that diffusion is taking. If, for instance, all the species are moving with the same velocity, right, then we will easily verify that the average velocity, whether you consider the molar average and the mass average, they will be the same, equal to the species velocities, and then we conclude that there is no diffusion taking place. The diffusion here is regarded as the difference between the actual species velocity and some average velocity. That is how we regard the diffusion. And now the other diffusive fluxes can easily be defined. We have J alpha, right, as simply C alpha U alpha, and then J alpha star as rho alpha U alpha star. So this may be regarded as the molar diffusive flux of species alpha with respect to the mass average velocity, and this may be regarded as the mass diffusive flux of species alpha defined with respect to the molar average velocity. These two are the most commonly used, especially because the Fick's first law has a very direct representation and simple representation in terms of these diffusive fluxes. But of academic interest, these diffusive fluxes may also be considered. Even we look for an exam problem or something, we have to know how they are defined. So notation should be clear. The notation is using commonly what is used in textbooks, including words today. Small j refers to a mass diffusive flux. That means the diffusion velocity multiplied by the mass density. Because a capital J would mean that the diffusive flux is formed by using the molar concentration rather than the mass density. Right? And then the star, if it is present, would indicate that the diffusive velocity is calculated by the difference between the actual species velocity and the molar average velocity. If the star is not present, right, then it would mean that the diffusive velocity is calculated by taking the difference between the actual species velocity and the mass average velocity. Right? So that if you keep that in mind, with the notation, you won't get bogged down as to which is what. Right? So anyway, these are merely definitions, and so now we have to do the same thing as what we did. C alpha will be substituted with X alpha times C, and then I will write C B star as C times, I have to substitute everything here in this equation. C alpha B alpha, I will write it as C alpha times B alpha minus B star plus C alpha B star, and this clearly can be written as A alpha star. When you substitute all of this, and then the equation that you would get, I will write it down. I am not going to derive any good exercise for you to derive, try to derive. What you will get is the equation analogous to this. Simply erase all of this. Final equation would be C times E star X alpha by dt plus the divergence of A alpha star is actually given by R alpha. This is for each alpha. These equations can be written minus X alpha times alpha equal to R ignore reactions, if I say that only diffusion is taking place, so there are two phenomena that come into play when you have multi-component mixture. One is diffusion, which will automatically be there, right? And the other is, because in general we expect each species is different, so we will be moving with different velocities under the same conditions, so you expect to have diffusion, the way we have introduced. Reactions may or may not be occurring. You can easily consider many cases of diffusion where reactions are not occurring, for whatever reason, right? So, in which case, I can simply make this to be zero, this will also be zero. So, effectively the distinction between this and this gets reduced a bit, right? And what is V star? V star is, you can easily guess, it would be d by dt plus V star dotted with the gradient operator. That is the substantial. There are many substantial derivatives. You can also define a substantial derivative for each species, which would be d by dt, the partial sign, plus d alpha dotted with the gradient. We haven't encountered it. You can easily define that. Right? So this is what we had, and this is equal to 0. Now, looking at it from the whole picture, we are now considering the mixture. Right? So we have now introduced 3 equations. Just as we had the continuity equation was a single equation. If we take the single component, just look at the continuity equation. Density is one of the variables, and then the velocity. There is only one velocity. The velocity is one of the variables. It has 3 components, so 3 variables. There are 4 variables, and so to solve for the velocities, we need the momentum balance, right, which will give the Cauchy's equation of motion and so on, the Navier-Stokes equation. They provide the equations to calculate the velocities. Of course, we also have the question, and we've seen, the distinction is there, but in principle, if we just look at it as compressible fluid, the density is a variable. Then the 3 components of the velocity, 4 unknowns. Now, there are C densities, capital C number of densities, so that is C variables, right? So look at the number of variables, C plus, right? And then 3 times C, which is C velocity, species velocities are there. Don't look at it from the diffusive flux, but look at it like this. This is the basic, this is being written for a purpose. It's a very special purpose, as we will see, right? So, 1 variable here, and then 3 variables here, because there are 3 components, right? 4 variables in every continuity equation. So, the total number of variables is actually 4C. But I have written down only C equations. Right? So, we need effectively a momentum balance for each and every species. Right? Now, common treatments of mass transfer avoid that complication, because it is possible. Obviously, that would be the natural step next. How is the momentum balance going to be for each species? Right? So, if you have a form, just as we can propose a continuity equation based on the form of the single component, some additional terms have to be added, taking about reaction. The same way, we will find the momentum balance requires additional terms to be taken into account, because when we consider the force acting on a species, we have to, because momentum is basically a force balance. Rate of change of momentum is the net force acting on the body. Right? Now the body is composed of different species, so we would have to isolate each component and consider what would be the forces acting on each component. And so each species will not only have forces exerted by a species of its own type, but also by species of other types of components present. All that has to be taken into account. But traditional treatments on mass transfer, especially in chemical engineering, avoid that by proposing models for the diffusive flux, which we will see a very special instance, and it cannot really be generalized very easily. So we will now take that up first, right, by first considering the case of a binary mixture alone, right, and then we'll see how it is to be generalized to more than 2 components. Binary mixture means 2 components. So a binary mixture, it proposes models for the diffusive fluxes. So now the Fick's first law can be introduced. We'll see how that is used to solve the problem. Again, we cannot give a complete solution of the problem, but we can still see some special case. Fick's first law in terms of the mass average velocity based diffusive flux can be expressed as minus. So I'm going to consider only alpha either is equal to A or B. Right? So I'll write it for A. Now, JA can be written as minus rho DAB times the gradient of the weight fraction of A. This is the total density. This now it is a new coefficient called the diffusion coefficient involving components A and B and the mass fraction. Now you can ask, what about JB? Right? You will now see for a C component mixture. By simply add up all the diffusive fluxes. Right? So this will be sum over alpha equal to 1 to 0 alpha u alpha minus u, because that is doesn't have any alpha in it. So clearly this is rho alpha u alpha sum over alpha equal to 1 to 0. This is rho times u, and they are, B alpha minus B. No u that we have defined. Right? So this is sum over alpha into 1 to 0 alpha B alpha minus rho times B, which is clearly equal to 0 by definition of the mass average velocity. What it means, the diffusive fluxes are defined, but all the diffusive fluxes you can see for a C component mixture, only C minus 1 of them are independent. Right? Because sum over alpha into 1 to C is 0. Similarly, you can show that sum over alpha into 1 to C, J alpha star will also be 0. But for the other two diffusive fluxes, it is slightly different. We just add them up, they won't be 0, but certainly they can also be shown to be not all independent. So if you have a C component mixture, by purely definition, only C minus 1 of the diffusive fluxes, right, are independent. So that is for a binary mixture. Once I propose a model for JA, right, automatically JB is determined. AB is equal to minus JA. Now what is the result of imposing this Fick's first law on the continuity equation? Right? So we now write that 2 times expand this plus the divergence of minus rho DAB is equal to, now on consider only the case where there are no reactions. Right? We focusing only on diffusion. Whenever we want to write the consider reaction, will add that term. That's not very difficult to do. So that's just going to be one additional term. Right? So now this is obviously becomes easier to reduce when you have, because the rho need not be constant with the position. We need not be constant to move the body. Right? Certainly DAB may also depend on the pressure and temperature and so on. But how do we assume that rho equal to constant, right? And DAB is also a constant. That can certainly happen. It can very well happen that diffusion is taking place. The total density is approximately uniform through the system. It's not such a restrictive approximation. It might be valid in many cases. So we vaguely, right? And so then we get, in that case, E is minus rho EAB, and then the divergence of the Laplacian of WA will be, I'm sorry, not the gradient of WA will be Laplacian. So rho can be, and then I get this called as a Fick's second law, right? But however, you will often not find this term. So further, if I assume that the mean velocity is approximately 0, this again is possible when two components are diffusing, but still the average velocity, if you look at it, speaking, they're diffusing in opposite directions, basically, right? So if that is the case, then we get some, this has to be A only. And you write it for A. So I am looking at it only from a binary sense here. If B equal to 0, this is the most common form of this. I just want to get to the very well known form of the so-called Fick's second law. You can see for the general equations they follow all these assumptions 1, 2, and then 3. We get the famous Fick's second law. It can happen only on the further assumptions, constant rho and DAB, and the mean velocity is approximately 0. All these are approximations. So we can also write this, since the density is constant, I can multiply both sides by rho and take it into the derivatives, right? And this is equivalent then, but not otherwise, to dOA by dB, which is equal to dAB. And it's very possible to show then that when you consider the molar, the equation in terms of the molar variables, there you will find, again I am considering no reactions for the binary case, you will get that if the condition of C equal to constant and dAB again constant and B star equal to 0, right, we will get dXA by dt is equal to dAB. So those actually slightly different set of conditions, because the mass average velocity being 0 probably may not mean that the molar average velocity necessarily being 0. It seems like you are having two different conditions, but effectively the same type of equation. You get the so-called Fick's second law from this. So now we will see how these equations may be used in actual simple problems. We will take up 3 or 4 problems and illustrate, right, how these equations are to be applied. And also see, more importantly, we don't have the time to carry over the larger problem in mass transfer, which is to actually solve for the velocities, and which would mean I have to introduce a species momentum balance. But typically what is done in most of these simple situations, you will see that some approximation is made which effectively means you are specifying what the velocities are based on the physical situation. So then, with the use of the Fick's first law and the second law, whatever we get, we can easily solve the problem and obtain the composition profile. Now the next question is, what happens when there are more than 3 components present? What would be the form that the Fick's law would take? Right? Because that is more important. Normally we have at least 2 components has to be there for a multi-component, but typically we have many components you have to see. So naturally we see that these kinds of equations are very limited. They cannot really help you solve many practical problems. You simply point out in which direction the stabilization will proceed, and that would be the mark, the end of the course. We meet again definitely tomorrow. Right? Tomorrow's class will be there, and then we decide whether to have one class next week or not.